only electron microscope can be used to observe nanostructure. Okay, it's too small. You cannot expect you can observe it under light microscope, okay, or optical microscope. Must be scanning electron microscope. Alright, application. Since whatever it is, the size, okay, it must match with what you want to actually make it interact, or make it detect, or make it trick. Okay, so there are the things that you have to sort of like think. Use it to identify location of cancer cell in the body, okay, because we can detect from outside. Nanoparticles, we can use it to deliver chemotherapy drug directly into cancer cell, right? So basically, have any of you see the cancer drugs? That chemo drugs that they use for chemotherapy, have you seen it? Have you visited people with cancer or hospital? Okay, so normally in hospital that treats cancer patients, they have hazardous beams, something like that. So all leftover cancer drugs, it must be split. It cannot be, they don't dump it in normal rubbish bin, not with other, not even with other sort of like hospital waste, no. Okay, because cancer drug, it's painful. The infection is irritant. So that's how hazardous. Even when we touch, many years ago, we deal with cancer drugs. Of course, we will advise to wear gloves, but of course, sometimes you want to feel it. No, okay, we can really feel when it's interact with our skin. That's how hazardous the cancer drugs. Okay, so that's why it's like imagine if we cancer in the colon, for example, they make it sort of like a chip, so if you reach directly the colon, for example, there are many ways. For example, for breast cancer, they make it like a pot, okay, and then they have wires that connect to the location, so it won't sort of like affected other part of the body and killing those normal cancer, normal cell. Okay, so that is the thing why we use most nanoparticles for chemotherapy drug to detect, to sort of like kill cancer cell. Alright, and then nanoshell. Okay, so this is another option. They can actually coat, have this type of nanoshell, so it will be heated from infrared source. So you have nanoparticle, when shine to infrared, okay, it will cause spike in temperature for to kill cancer as well, cancer cell. Alright, and they can use nanotubes to actually repair bones. Okay, when people have sort of like, of course, broke or crack, okay, they can use nanomaterials to actually repair it. Okay, nanoshell as cancer therapy. So this is how they actually use it. So they have cancer cell and they have nanoshell. This is an example only. So they can actually, the cell actually will engulf all this nanoshell. Okay, so this red color or pink color is healthy cell. So this healthy cell won't be affected. Okay, because this nanoshell is already packed with biomolecules that will go only to cancer cell. Alright, so after that, this we use infrared to actually kill this cancer cell, because these nanoparticles will produce high temperature when exposed to infrared light. So this cell will survive, but only cancer cell will be dead when exposed to infrared. Okay, so these are the concepts that they use. Alright, so again, how are we going to do it? First is synthesis of nanomaterials, like the shapes that I mentioned before, size, types of material, we decide here. Then you want to have what? Whatever dimension, whatever colors of nanomaterials, or do we need to have magnetic properties, we decide here. And modification, do we need to have we want it to be pure. Do we need to have carboxyl outside, or do we need to have amine, for example, or it is directly ready? Because some chemicals, when we do synthesis of nanomaterial, is already ready for conjugation. Okay, so those are the things that we need to decide. And then we have to think about nanobio interface engineering. So how does it actually work? Okay, can it be used directly or what? Right? And now people are talking about integrating nanotechnology. For example, even though nanomaterials, if we conjugate with enzyme, right, GOX, glucose oxide, it will recognize glucose already, alright? But the signal could be low. So can we amplify the signal? Right? So there is convergent technology. So we use another another technology to amplify the signal. The same thing that people use in most of the disease, because certain disease, the concentration of the proteins is very low. So if very low, you cannot detect. If you see normal lipstick, so we need to amplify it. Okay, so to amplify it, we need to use convergent technology. So normally we use sort of like amplifier, all those things. Okay, so nowadays we divide nanobiotechnology and nanomedicine. Okay, so all need to use many things. So nanobiotechnology is similar with what I said, but when it comes to nanomedicine, and we start to talk about biosensors, molecular diagnostic, personalized medicine, nanobio-pharmaceutical, and also drug delivery. So again, similar concept with what I mentioned, but they study more on use in the body. Okay. Alright, molecular diagnostic. This is the main topic for you, right? Because when you have patient's sample, what to do with it? Okay, that's what you doing. They recognize, they want to sort of detect certain disease. Of course, they have to take sample, okay, and then either protein or those things. But they need something that can recognize the protein that they actually take. Okay, so normally they use DNA or they use antibody-based most of the research in order to do that. That's why we call it molecular diagnostic. So molecular diagnostic, this is the very broad term. So that's why, like myself, I always talk about proteins. Okay, because when we talk about proteins, then of course it's include everything. Okay, antibody include what is that? DNA include, because some of the research here, the nanoparticles is conjugated with protein A, for example. Okay, that can involve protein, but because the protein can interact directly, some cannot, right? And then, have you done that on diagnostic? Which lab have you done so far? Not yet. Not yet. This is week. How many already? Yeah, that's soon. Okay. I expect because in engineering normally 2 weeks lecture, one that several weeks. Okay, one that so that's why now it's already almost half. Okay, so I expect you have done certain labs already, so you can understand better. All of you, what are your background? Okay. Alright. Okay. Alright.
Nursing medical.
Okay, and you?
Examination medical.
Okay, so most all I would say should be able to understand by the test today. Okay, only I think I know is nanomaterials part is quite challenging, but you don't need to understand about nanomaterial. You need to understand about interaction, how these nanomaterials can be used as for biological application. Okay, so IFOP are working on detection, mostly diagnostic. Okay, and the diagnostic kits are many types of diagnostic kit. What you see on the corridor, for example, mostly lateral flow. Okay, but there are some that work using lights, optical. Okay, some electrochemical sensor, many types of sensors they are working on. So the concept are similar. So basically, when they have diagnostic kit works because we use it. Everybody use it to detect COVID-19. So that is the concept. Alright. When Inform already has several commercialized diagnostic kit even before COVID-19. Okay, they already have it. So they already have line for it. But the only thing they don't have biosafety facilities that can do the research for virus. So they're dealing more on bacteria. It's okay to do it there. But they have very good sort of like collaboration with certified lab, hospital, or this thing. So that's why in Inform, whatever sample that you want, it is possible to actually get it. So easy for them to do work on sort of like to detect certain virus and bacteria. So for diagnostic, molecular diagnostic today, so that's why we have Inform in Kelantan because we have HUSM, hospital USM. So we get sample mostly from HUSM. Okay, so that's why it doesn't matter. You want to have the sample in the form of blood, okay, stool, or whatever it is possible to actually get. Okay, around here also they have many freezer that contains many types of sample for infectious disease. So basically, if the disease is not most of the research here is the cancer or infectious disease. If it's not infectious, it's no point to actually do it. Okay, so that's why the research in diagnostic kit for COVID-19 have outbreak. Okay. for COVID-19, they put it 15 minutes. Most. Why? Most, yeah. Am I right? Most. They put it, wait for 15 minutes.
Because the COVID-19 is very speed spread.
Yes, but this is 15 minutes is the term that the guideline that FDA give. Okay, it must be less than 15 minutes, or else you cannot call it rapid test. So that's why all they will elaborate less than 15 minutes, or else they cannot sell with the similar that term. Okay, so that's why they don't say, oh, I can detect 2 minutes, 3 minutes. No, they still use less than 15 minutes because that is the guideline. Okay, and we need to understand as well. If, for example, I have COVID-19, you have COVID-19, mine probably take 3 minutes to detect. Yours probably take 7 minutes. For diagnostic kit, oh, it definitely 5 minutes, definitely. So that's why the guideline said must be less than 15 minutes. Okay, so that is the thing. Okay, what I want to show here, this is a market for molecular diagnostic. Back in 2007, it was 9 billion. Okay, at that time, 9 billion only. So when we talk about diagnostic kit, okay, we have the all the different types. The one give colors, okay, this one give sticks, but give you certain different color. So you have to compare with the sort of like the standard, right? And this one is give you the lines, right? Okay, what is the market now? Okay, global molecular diagnostic. Okay, we are here at 23 billion, right? The projection in 2022 with 10% improvement. Okay, imagine from 9 billion. They also divide it into infectious disease. Okay, infectious disease, this one, 38%, and this is oncology. So more than half infectious disease and interest nowadays to actually test it as fast as possible so that the disease can be treated. So that is the most important thing. We want to know it fast so that you can actually treat it as fast as possible. Okay, this is the concept. You have nanomaterials, okay, and then you functionalize the surface. Okay, so from there, we can put it. Okay, if I want to do the nanoparticles to give me color, okay, so I can put fluorescent dyes, for example, okay, or if I want to make nanoparticles, I can put PEG, I can put carbohydrates, for example. Particle directly. For example, I have one nanoparticle, just synthesize one nanoparticle, I simply inject into my body. It will cause blood clot immediately because our body recognize it as impurity. Immediately, okay, it will block everything. To make it sort of like biocompatible. Okay, and then we can also conjugate with tumor markers, for example. And nowadays, a lots of research has been carried out on using atom to detect. Okay, and then RNA also people have done, and a lot of research has been carried out on conjugate nanoparticles with antibody that will recognize certain disease. And they also conjugate drugs with nanoparticles or put the drug inside nanoparticles for fluorine. Okay, put drugs inside. Okay, but outside they. So this is how nanoparticles are being used for diagnostic application. This one I think you have in one part in your lab that they will teach you how to actually do this. So the concept is like this, similar with COVID-19. We have gold nanoparticles conjugated with antibody. Okay, and then this is the analyte. Okay, and then we have test line and also control line, and we have absorbent pads. So that's why the liquids will flow to this side. Okay, so this is how it actually works. Similar with COVID-19, if you have two lines. Okay, single line or double line. That only the results is valid, right? So because of COVID-19 also, now that you can see one dipstick already can detect COVID-19, influenza A, influenza B. Before COVID-19 we don't have that. We can't even find the dipstick for influenza in the market. It's so expensive at that time. If you go to private hospital, yes, we can get, but we charge it very expensive. Nowadays, we can get it less than, how much I bought? 500, but they have those for free. To actually produce one nanostick. Okay, so that's why they can sell it at 28. Okay, because the gold nanoparticles is just enough to produce those two lines. That's all, the red color, because it's carrier. Okay, that give the color. Gold, it won't interact with anything else because it is noble metal, and then you can use anywhere. The detection less than 50 minutes. Why people like it so much? Because the data they get is using naked eye. How you get the lines. Okay? So it is quick, flexible, and more sensitive. Okay, so this is example. Alright, so this is example of the interaction. So you have gold nanoparticle conjugate with antibody. Okay, so this is your analyte. So this is the interaction with antigen that you get. Okay, so that is how we can get these two lines. You conjugate gold with IgG and IgM can be used to detect malaria. IgG and protein A, it can detect HIV. Typhoid, we can conjugate with good anti-human IgM, IgA, IgG, and IgG can detect typhoid. Dengue has been reported to detect IgM and also human IgG. Use this human IgM and human IgG can detect dengue. Phobia, we use mouse anti-human IgG4. H1N1, we have to use this influenza A antibody, and also chikungunya IgM, right? And drug abuse also. Now there's a lot more in the market. Not only for methamphetamine, morphine, benzodiazepine, also for crypto, right? And then before COVID-19, the most common is pregnancy test at that time. Before this, it was very expensive even for drug abuse. Drug abuse before COVID-19, I think the cost is over 50 ringgit per test. Okay, but nowadays it's reduced a lot because of they know how to make it cheaper. Okay. Bio-interaction, okay, and then it can be called biosensors. Okay, this is the current interest. Okay, when we have materials, okay, can we have flexible materials? So it can be attached directly to the body. Okay, so the concept is we call it either you can have paper-based devices, flexible devices, or wearable devices. Okay. Example, of course, smartwatch, for example, that can detect other things, other information, or wearable glucose sensor. That is the thing. Can we get the reading using our mobile phone or using laptop or stick for data processing? Okay, like what is that? Lateral flow. You get the result, the current. And then the signal can be stored in mobile phone. So the more, but again, you cannot expect those from Inform only to produce this system. They must collaborate with people from engineering and computer science in order to do this. Okay, so like here, we have lots of grants. For example, they want to make certain product. If we see the team is only people from Baldino, we won't approve it because there's no way they can produce device. It must be people from computer science or engineering collaborate with them in order to produce that. Alright. So biosensors, any device, okay, it doesn't matter. Particles only, film, whatever it is that have reaction with biological sample and give certain signal. Okay, later I will explain more about what types of signal that you can actually get. Okay, this one is, if you say something like this, is definitely people engineering involved. Okay, because to make the device that give you a signal in current, like myself, I always see this is silicon, all those things, and I can see the electrical things. Okay, so that's the thing. The definition: you must have biological element. Okay, you must have transducer. And you must have detector. Okay? Or else you have the disease only. Or very much close to the disease. Okay? But what is that? That is only biological element. Okay? If you don't have transducer, okay, then it cannot be detected. It must compose of the full sensors, then only we don't want something, it can sense. But how to read the signal? If, for example, I said nanoparticles only, it can interact with biomolecules. But yes, it goes to agglomeration, but can you see? Cannot see. Okay? That's why people put on paper. They put in the flow, oh, I can see red color. But if I drop it directly in the solution also, it already have interaction. But to make it readable, then to translate it into result that everybody can understand, there is biosensors, there is sensors. Okay? From whatever analyte, from whatever disease, until you get the result. That is the most important thing. Okay? So before I proceed, I think we break first until 10:15. Okay? You want to go to the toilet or something? Have you been to any lab before?
Inside the info.
Huh?
Inside the info.
Yeah.
This, like in the first semester, we had some lab classes.
Okay. Alright. So this is your second semester?
Yes.
Quite senior already. You know the way around. for biosensors, I mentioned before, okay? So biosensors, it must have biological element, it must have transducer, it must have analyte, of course, detector. So the concept is like this. This is the analyte, okay, variable disease, alright? And then you must have bioreceptor. So this is why, for example, nanoparticle is always being conjugated either with enzyme, antibody, microorganism, or something else, right? And then transducer. This is sort of like when this interaction happen, what exactly the signal? Okay, so can it cause electroactive substance? Okay, or can it cause pH change? Can it cause heat? Can it cause light? Can it cause mass changes? Okay, so from there we know what is the transducer that we can use, and then there is the electrical signal. For example, this is for electrical devices. Many types of this. It's not only about color that you actually get. Okay. So first component is vertical element. So it can be anything highly specific, stable under storage condition and immobilized. That is very important. You must know how to store the vertical element. So normally it's in the form of microorganism, tissue, cell, organelle, nucleic acid, enzyme component, receptor, and antibody. So that's why in most of the lab in form there are many types of freezer. Okay, so that's they actually store all this. Alright, so the concept is, for example, enzyme and also substrate. So this is active sites. Okay, second component is physical-chemical transducer. So this one is very important because we have to choose which system that we actually want to use. Okay, we cannot expect, okay, biosensor, I only want to know kind of thing is more, because there are many types of sensor. Okay, so electroactive substrate. So this one electrode, this interaction we actually use for microfluidic system. Electrochemical sensor, many, okay, for this. And then change in pH. Normally we use semiconductor pH electrode. Heat we use thermistor. Okay. Light we use photon counter, and mass change we use piezoelectric. Right. So this is the detector. So the detector is like complete set like this, like in glucose sensor. Okay, those the reader. Alright, the reader comes with certain numbers. Okay, so that is the thing that people want, because the development of certain sensor, for example, electrochemical sensor, they only make electrodes. But what is the reader? Okay, how people make money is the electrodes, because electrode is used once only. The reader you use for 5 years. Alright, so for example, if for diabetic patients, they test at least twice a day. Alright, and then the one case is 25 electrodes, something like that. So it won't even last them for 1 month, and they have to buy again. So that's how company make money. And they don't make money from this, from the reader, because the reader can be used for a long time. Okay, principle of detection. Okay. In piezoelectric sensors, is measured in the change of mass. Okay. Electrochemical, I think I hope one of your lab inform electric distribution, and optical sensor change in sensor also dark environment, then only you can see under UV, then only you can see quite a few under optical sensor, and also calorimetric, that if the interaction cause changes in temperature, and then you can use this system. So many. Among these, inform those electrochemical and optical are what we use. Okay, because even sensors in biosensors in market mostly use these two principles as well. Alright, this one is just a bit about piezoelectric biosensors. Like I mentioned before, piezoelectric, when there is interaction, okay, mechanical interaction, it will generate electricity. If you give electricity, it will generate mechanical. That is the concept of piezoelectric. Okay, so in terms of biology, okay, interaction with biomolecules, it won't give you electric, okay, because it's normally looks mechanical, so you get the electrical signal. Okay, the same sensor we in engineering, we use it to get the mechanical. Okay, so there is piezoelectric. It can be vice versa. Interact with electrical, give you mechanical signal. Interact with mechanical, it give you electrical. So for those in bio, normally it's another way. So is there any changes when the biomolecules interact with piezoelectric material? That is the most important thing in order to use this piezoelectric biosensor. And electrochemical sensor, this is electrochemical sensors can be divided into several types. One is amperometry, potentiometry, and conductometry. So amperometry, I think most use amperometry, movement of electron in redox reaction. I think that we'll cover on this. Potentiometry, change in distribution of charge. Basically, what happened to that? So you will get the signal from there. So conductometry is impedance. There are many people use this conductometry as sensor, but it is, for me, it is not as accurate as amperometry and potentiometry. Okay, it can be used to validate the result, but to sensor, so optical biosensor is colorimetric change. So basically, if you have the interaction, you will get the color. If there is no interaction, you don't get color. Okay, so example is this, right? Okay, there are many things, many types of nanomaterials that you can use to do these types of detection. Okay, colorimetric. So colorimetric, normally for this type of sensor, you will see something like this. Okay, electrodes, 2 electrodes, because it must be when the interaction occur, there must be temperature change. Okay, if you are talking about something change, it must have some reference. So that's why it always have to. Okay, as a reference. So what the reading that you get is the changes into about the sensor, biosensors. One is the analyte. Okay, so normally we just call biomolecules, but it can be protein, toxin, peptide, vitamin, sugar, metal ions, all those things. Okay, sometimes we forget. Why metal ions is part of the biosensors? If your blood got contaminated, if you accidentally drink or eat food that contain heavy metals, for example, is already in our body. So we need to know how much the metal ions in the body. So that's the thing that we need to actually have this. And then sample handling, how to deliver analyte to the sensitive region. Okay, remember the dipstick that I showed before. At the back, it has absorbent pad, right? How to deliver. So those are the things. Sample handling, how? So it must be convenient not only for us but for the patient also. Okay, you cannot, for example, now saliva testing is very, I would say, famous, but that is not 100% accurate in terms of testing. Okay, for example, for typhoid, they take sample from stool, but the process, okay, you cannot get sample directly from toilet or something. Okay, so that's the thing, how to process the sample. So because of COVID-19, people see very convenient to actually sort of like detect the disease. So I can see many types of dipstick try to make that requirement, either use saliva or blood. Okay, but not all disease can be detected by these two. But that's the thing. And then even they are trying, okay, can we get sample from sweat? Another thing. Okay, but it's not easy to get sample as well. You cannot force people to get sweat, so that's why still lots of work has been carried out to actually in terms of handling of the disease. And for example, another example, typhoid. We don't get typhoid outbreak every day. So, for example, in 1 year, probably 1 or 2 typhoid outbreak. When we say outbreak, normally 40 or 100 people got diarrhea or something like that. Then they need to check for typhoid. Okay? So, that's the thing. But people that want to do research on that, you cannot wait for another year for another outbreak. So, how to store that sample? Okay, so that is very important as well. Okay, it's not like COVID-19 was very fast in terms of diagnostic delivery because the sample is massive. So that's why it's massive. But other disease, it's not that easy. Okay, of course there are rules to even collect the sample. It's not simply okay, can get the sample, something like that. Okay, unless the sample from our body. That one, luckily they have regulation that allow researchers to use their own sample. That one is allowed. But for disease of glucose body sensor, the researcher use their own blood for testing. Because of that, so they take blood before eat, after eat, after dinner, all those things, because it's allowed under ethics, human ethics. But I cannot take your blood to test the sample. I have to go through an ethics committee in order to say, okay, I want sample from 40 patients or 40 people. I need to go to ethics. Okay, but I can take my blood and declare directly, this is my blood on this thing. Okay, so that's the thing. It's not easy. Okay, detection and recognition, you need to know how to scientifically. No. How do you know? Device, okay? Because it gives you current and voltage only, okay? So what happens is that if there is interference, can you differentiate? Because it's changed in the value only, okay? Unlike those, for example, dipstick, if it's interaction with something, it won't give you color. Because we have already tested for its sensitivity and specificity. But in electrical sensor, of course we test, but it's not as accurate as this. So far that I've been through. Okay, we tested, and then because the changes is only in terms of graph, in terms of value. Okay, you might get the interference. Okay, so it's still don't limit yourself with the diseases or infectious disease that people are working on. Okay, don't forget, other than clinical diagnostic, we also have food and agricultural process. We have food and agricultural process. We have environment, okay, air, soil, water, detection of water agent. Basically, unwearable biosensors, okay, more than 4.5%. Infectious disease testing segment 2.5 billions. Optical more than 7%. Research lab segment 6. We can expect in terms of development of biosensors. Alright, this is the thing that I want to show. Okay, blood glucose testing. Can you see the 2022 and 2030? So inside, that's why it's important, not only for blood, for food. Because the food that we consume actually cause diabetes. So that's why they start to sort of like have a regulation. What are the maximum sugar that you can put? Okay, so there is the thing. But this one, if we see this, we can expect how many patients into 2032 that will have diabetes. So there, this is the issue now. Cholesterol. Okay, okay. Blood gas analyzer. This is important as well. Because we don't want it, our blood to contain too much carbon monoxide, or else it will kill our brain. Okay. Pregnancy testing, we thought it's a lot already, but in the market not so much. Drug discovery, infectious disease, so little if we still compare to glucose. So that is the market. Okay, so that's why in most pharmacies, blood glucose sensor. Okay, alright. But nowadays is because there are so many diseases nowadays, but everybody still depends on hospital, depends on equipment to detect it. Can we detect this? The kids only. Okay. Normally, what we want is like, okay, this patient might have cancer. Okay, that's the kit to confirm, then only go to the hospital. So they get sort of like shorter time to actually detect certain disease. Okay, because to ask people to go to the hospital already take months, unless they are very sick, then only they want to go. So that is why it's important to actually detect. Application in this one, like I mentioned before, okay? Food analysis, study biomolecules, drug development, crime detection, medical diagnostics, environmental monitoring, quality control, okay? Industrial process control, detection system, and manufacturing pharmaceutical. So that's why I've seen graduates with PhD from Info work in glove factory. Glove. That's it. Glove. Okay. So apparently they are developing glove for students. So there must be people that are good in environmental interaction to actually do the work. Okay. So don't limit yourself in terms of this. Okay, the next topic is drug delivery system. Like I mentioned before, nanoparticles can be used in drug delivery. There are options. The The this is example of drug loaded micelle. So you have micelle structure, it's like polymerase things like that. So they can actually entrap drug inside. Or this one is liposome, okay, quite a lot is already in the market, and they can entrap both hydrophobic and hydrophilic drug inside and in the middle. Okay, this is drug loaded nanoparticle. This is drug loaded vesicle, quite lots. And we have this one is organic. Okay, this is how they actually put nanoparticles in the structure. Okay, so basically the concept is, because this is drug delivery, how to deliver. So synthetic identity, and then biological identity, and physical chemical. Okay. The amount. What is the benefit of it? First, you need to reduce the concentration of drug. If I take the drugs directly, I have to take 2 tablets. If I use nanomaterials, do I need to take similar or lesser? If I have to take similar, no point. Okay, it must be lesser. And then it must have less harmful side effect. I mentioned before, chemotherapy drug is very hazardous. So when we put it in nanoparticles, okay, it must be less toxic, or it be sort of like only release the drug when it reaches cancer cells. So that is the target. And then normally for drug delivery based on nanoparticles, we call it also drug targeting, delivery, and release. Okay, so the drugs entrap with chemotherapy drug, for example. Okay, they already have drug inside it. Outside, they put it biomolecules that recognize the cancer cell, so it will deliver there first. Okay, as you know, the cancer cell is the temperature is several degree higher. They about 42 degree. Yeah, maybe 57. So they make a drug delivery system that can only release at that particular temperature, 42. So it won't release at other parts of the body. Okay, another thing that they do is that is targeted delivery. The nanoparticles, for example, it's has magnetic materials. So they shine the cancer site with magnets. So this drug, because it is magnet, it will go to magnetic field. Then only they will kill them. Okay? So there is another option. So that's why we call it target deliver and release. So it won't be released throughout the body. So that's why 20 years ago, people died of cancer, not because of the cancer, because of the side effect of the drug itself. Okay, so that's why. Okay, the main goals of drug delivery is their stability. Can we improve the drug loading? Can we improve the targeting, transport, release, and interaction with molecules? Okay, toxicity is the main issue as well for drug delivery. So these are some other options. We have to know where do we target. We have to mesh in terms of size, and then we can choose whatever nanomaterials. So normally for drug delivery, we prefer organic ones, majority organic, because organic, it will sort of like escape from the body after a few days. Okay, if you use, for example, inorganic, okay, if iron is okay because it is part of the body, and then there are ways to actually remove it. But other types of inorganic, how can we make sure it's accumulated in the body? That is also the challenge. Okay, so not everything can be used inside the body. So the similar concept with the stick, okay, you can have put it inside, put it both inside, outside, and then you can also make the drug itself in liquid crystal, nanocapsule, nanospheres. Okay, the concept is like this. Put inside. And then you can put what is that, antibody that recognize the cell, okay, and then you can put surface capsulize it with peptide or nickel or something, okay, so that you can release them. Advantage drug delivery of system of this is small, okay, less than 100 millimeter. Normally drug delivery we use less than 50 nanometer. It depends where you want to actually release. Normally, we don't make it lesser than, I would say, 2 nanometer. Okay? Not even 5. Why? We don't want it to go to the brain. If it go to the brain, it will change your DNA, everything. It will change the code unless it's for brain cancer. Okay? If it's nothing that serious as brain cancer, you can use anything that is small. We don't want, okay, that is the concept. We don't want anything smaller than blood brain. Okay, it's very it will kill us faster than trying to actually deal with the disease. So because it's small, it has high space area, and then we can put more drugs. So that's the thing why we want it. And we can also attach specific target cell organs that recognize it, help to avoid fluctuation. Okay, this is another interesting thing. For example, tuberculosis drugs. Tuberculosis treatment, it takes up to 6 months. So once we get TB, it takes at least 6 months for the to take. And of course, who wants to take medicine every day for 6 months? These people, after 1 month, they don't cough already. They are okay already. Okay? So, this kid, the medicine, what happened? Next few months, they already, yeah. Okay? So, that's the thing. Normally in Malaysia, if the clinic already know this person get tuberculosis, so if they don't go to clinic to take the next level of medication, they sort of like make sure this person go to clinic. I don't remember every day or every week to take the medicine because they must complete the lines. Okay, and imagine the drugs is not 1 or 2 pills, it's a lot of pills for TB. Okay, so that's why I would say the patient's compliance. Who wants to take more than 2 pills a day? Okay, when they don't feel sick. If we have fever, we have flu, yes, we take medical. But these people, it's in good condition. So the drug delivery system is aimed to reduce the dose. That is the most important thing. And to do that, the drugs must be slowly released, the drugs, get the drug released. So we don't have to take it regularly. So that is another aid that we can do. So the new drug delivery system is must improve the patient compliance. So meaning that, okay, patient, okay, I'm okay to take this. Improve outcome. If the outcome similar, 6 months. If I take Nanobase also 6 months, what's the point? Okay? Reduction of adverse effect. Like I mentioned before, cancer, chemotherapy drugs. If it's not coated, right? So it is very hazardous. But if they would use nanoparticles, it doesn't, it reduce the adverse effect. So patient will like it. Improvement of patient acceptance. Avoid costly intervention. There is a thing. Sometimes you give the delivery and then have to use other equipment to take it. So it's not possible as well. Alright, so other thing is the release profile. It must be biocompatible, biodegradable. We don't want another particle to accumulate in the body because we don't know what will happen in the future. Roots. Okay, this is very important. If you want to study drug delivery, expect at least 10 to 15 years to commercialize. Okay? It is interesting topic, but you could spend the rest of your life doing the same thing. Alright? Because it starts with lab. In drug delivery system, okay, according to FDA, the record is since day one. You must provide the records. Okay? So it's first is choose the materials must be biocompatible, biodegradable, route of administration. Okay, to swallow it or what? Think how the drug will be released in the body, diffusion, temperature, magnet, drug release profile, release with time, release with temperature, release with pH. Okay, because in our stomach, the drug we should target it release with pH 2 or something. Okay, so it doesn't spread in the body. Agglomeration. Okay, normally we study with start with something sodium chloride, and then in my serum need to study agglomeration. I mentioned before. If I have a I cannot simply inject in my body. It will agglomerate and cause swallow immediately. Okay, for example, when you trim your roses, okay, if you get poked by the spot, you can see, right? Because that interaction with our body, we recognize it as harmful to our body. It will cause swelling. And you have to study how long drug will retain in the body, safety in terms of in vitro and in vivo. You shouldn't do in vivo in animal unless you have the result in vitro in the cell that says, oh, it is non-toxic. Okay, it's so cruel to test directly in mice when you don't have in vivo data. Okay. USM won't allow it to do that without in vitro data, but some universities or research centers allow it. So that's the thing. Sometimes it depends on our ethics. Alright, so for normal people like us, we thought, okay, route of administration only oral. Okay, there are many other types of delivery. So put, when you want to do this, put something that is, try something that is acceptable by the patients. Okay, nowadays I can see a lot of patients, patch, creams, all those things. It's better, so people don't suffer basically. Okay, not only that, after we finish all those things in lab, okay, a lot of things in imaging of agent carrying in vitro, optimize synthesis, fabrication, validation, optimize delivery route. So many in vitro. Then only you can go to in vivo. Then only preclinical 1, preclinical 2, preclinical 3. So many. Okay? So in Malaysia, that's why very little commercialized drug delivery, because we don't want to spend 15 years of our life to delivery unless it is very harmful disease. So that's why most of the drug delivery system using nanoparticle is for cancer, I would say. Okay. Alright, so you have to consider dose. Dose must be low enough. potency, structure, physicochemical mechanism. Okay, because we don't want to cause harm to our body, and then the stability in with different environment, because everybody has different thing. We don't know if it works in my body, it might not work in other people's body. So that's why when they do preclinical tests, normally according to region, okay, Asia, Africa, UK, Europe, okay, it's not. That's why normally preclinical, those normally third world country, all those things have to sort of like do that first, okay. It's always like that. And again, those that do preclinical, they are the one that will get the benefit first. Okay, so there is of course pro and cons when it comes to preclinical. Sometimes that's why cancer is okay. Why? Because this patient, if you treat or not, they see that. Okay, if you treat, the potential to live slightly higher compared to if they don't get treated. So that's the thing. Toxicity, very thing, very important thing. Toxicity is one thing, immunotoxicity, there is another thing that must be proven. Okay, so there is many things about safety that need to be done. In lab, normally we do cytotoxicity, ICP, yeah? So 50% of those must test first before we use in anything. Okay. Alright, the last part is theranostic. So what is theranostic? I like the concept of theranostic. It's similar with what I show you. Okay, so it's like similar with drug pellets. Okay, I can have it fluorescence probe outside that give me color. Okay, I can have a targeted ligand or antibody, for example, that will recognize the cell or will react with the antigen. Okay, and I can have radionuclide that will do the job, the treatment. Okay, and drug payload, it also releases the drug over there. Okay, so this is sort of like full complete set of device, but this is actually drug delivery. Single nanoparticles that carry everything inside. So what happened? This is the real one. Okay, so you have this. Okay, nanoparticles, since it recognizes only cancer cells, so it will stick there, and then it will interact with radioisotope. So that is the target delivery. So theranostic, so combine specific targeted therapy based on specific targeted diagnostic kit. So basically, they attach directly to the medicine that need to take the patient directly. Okay. So for me, I really like this concept basically, and it's getting more popular since 10 years back. But the latest 5 years is a lot of work has been done for this one. Okay, before this, radioisotope was supplied that separately. Okay, so how many treatments you have to go through? One is for radioisotope therapy, and then drug another. So it's you need to get lots of treatment if we do one by one. So this one is lesser treatment, meaning that visit to hospital can be reduced. So that is the thing. Okay, for now, for chemotherapy, for example, they have 12 cycles. Okay, so have to go 12 times. Okay, if they feel sick, have to go again. So that's the thing. So the idea we can have theranostic is like to reduce number of visits to the hospital. Okay, can we do that combination? Okay, so this is the concept. So they have sort of like theranostic material for molecular imaging and target therapy. So they inject into the body, and then this one, the theranostic molecule go to the cancer cells. Okay, so we activate that. So if there is cancer, and then only be activated. If not, and then it will be taken out from the body, stripped from the body directly. Okay, it will reduce the time basically. So this is molecular imaging and therapy. So when they diagnose cancer, so basically they inject. Okay, so similar with MRI, check, and then because of this is targeted menstruation, it will accumulate here on at cancer cells. Okay, and then you can actually kill the cancer cells only. Alright, so that is the concept that, of course, we want it.
Doctor,
Yes,
what's between this and drug delivery system?
drug delivery. Okay, this is the combination directly. That's why we call it theranostic. Drug delivery, not only for cancer, drug delivery, TB also drug delivery. Whatever it is, whatever the disease. Okay? But now they want to have one drug that not carry the drugs, recognize the cell, and also if you need to do radio imaging, okay? Okay, either to get the image in one. The concept is similar. You basically put something inside or put outside, whatever you want to put. But you have to know, do you want to, that means radiation. Okay, you want to radiate or not? If not cancer, there's no point to do radiation. Okay, alright. And remember that for cancer, even cancer treatment, not everything need to be radiation. Okay, you can use chemotherapy only, radiation only, or something like that. Okay, so which one? Like this one, it not only have chemotherapy drug, it also can have the radiation. Normally the cycle is like either chemo first, followed by radiation, or chemo, radiation. So can you imagine how many times to go to hospital? So the idea is, can we do it at one time, visit to the hospital? That is the thing. So that's the thing. That's why I asked, have you visited cancer patients before? It's because it is sort of like daily. Chemotherapy is day care. So you go in the morning, they do the chemotherapy, and then you go back in the evening. So imagine if you have to do it 12 times with those side effects, repeating side effect, and radiotherapy another session. So imagine how say in terms of patient acceptance. So that's why there are patients that halfway they don't want to get treated already because of the side effect, obviously. So if we combine this, can we reduce those side effects? So that is the idea of therapy. Do once for all. Okay, probably from 12 cycles we can reduce to 5, 6 times. Right? So that's the thing. Theranostic, I think, is already in the market. But again, it won't reach all countries, certain countries. Okay? And it is not cheap, basically, I would say. Okay? So, alright. So, not only it has chemotherapy drug, it has something that we can image if the cancer is still there or not. So that's the thing. Or else, after that, you have to do CT scan. If you heard right, after chemo, have to go again for CT scan to see either the cancer is still there or not. And then repeat for 12 times. Repeat the same thing for 2 years until they say, okay, you're cancer free. So that's the thing. Okay, can you have the drugs that deliver, treats, okay, it need to be chemotherapy, radiation, and then image it directly. So that's the idea of the diagnostic. Okay, of course, diagnostic not for those mild disease. So now they call it, remember the term personalized medicine? Okay, so now they call it personalized, what is that? Theranostic. Personalized therapy for cancer. So, sort of like, it might not be suitable for all types of cancer, but they need to choose which one. Because not all cancer drugs for all cancer, it's site specific basically. Okay? This one is magnetic field. Okay, example. Okay, they use iron oxide. Okay, because iron oxide under magnets, magnetic field, for example, it will be the kill cancer. Okay, so if we have diagnostic strategy, magnetic So being able to visualize using magnet, okay, the same. Okay, you inject iron oxide, so you can image the patient using MRI, guided sights by external magnetic field because it is magnetic field. So I put it, locate the magnetic field outside the body, so it will be accumulate at that target site only, and then it can be heated that provide hypothermia that kill cancer cell. Okay, so that's why we use magnetic field for that. This one is already in the market. All right. Okay. That's the thing. In Malaysia, we always heard about chemotherapy, radiotherapy, but there are other options, but slightly either expensive, time. That's the thing. Okay, but the products in the market. That's what I can tell. So hypothermia concept. Okay, so once it's go to sites, okay, cancer site, so you can heat it up from 41 to 46 degree. So that's why it's actually infracellular. So that's why we kill the cancer cell. I think this one, the first patent was in the US. And the work was not US, the patent was in US. Alright, so there are the things that they actually can see. Protein misfolding, alteration, induction of apoptosis changes. Okay, they can image that. Again, there are lots of concepts. Okay, okay, one thing, the idea is like the exposure is 50 to 500 kilohertz. Is MRI region basically. Basically, we don't do MRI just because we want to do MRI. Okay, one thing is it's expensive. Another thing is it's also risky. Okay, so that's the thing. There is always debate. Can we do it? Even though we know all this benefit that we can get, but do we want to expose ourselves to this high frequency? Will it cost other thing? Probably not now. 5-10 years later. Those that already have cancer is okay. They don't have choice. But for a healthy person, do we need to take the risk? So that's the thing lah. Even though MRI it's can see everything, okay, but not everybody should do it. Alright, like my friend, she had to do CT scan. CT scan also similar. You have to inject contrast agent. She became allergic to that contrast agent. She ended up in ICU for 3 days. Imagine, for simple imaging, CT scan, you do it for 1 hour. Chemically stable, biocompatible, super parametric, low price. Okay? And then you can tune most of the properties. You can do surface functionalization, you can do conjugation. So basically you can do all. And where are the applications? Right? We need to use, normally it's being reported 10 to 15 nanometer. Hyperthermia, normally we use 20 to 100 nanometer. Again, we don't use those very small that will affect our blood flow. Okay. Immunoassay, biosensors, and MRI. Alright, 10 to 100 nanometer because you want to image the whole body, basically. Gold nanoparticles. Okay, gold nanoparticles, you can actually change the color. Okay, whatever the color that you actually want, and then the color also change with the shapes. Okay, so it can be activated by X-ray. That's why people use it for cancer treatment as well. So again, these are the properties of it. It's noble metal with less toxicity, biocompatible, able to mobilize. Okay, strong optical properties. So that's why even used on paper, you can see the lines. Okay, and protection against oxidation, maintains the stability. So basically, I remember during COVID, the test kit can stand for 3 months only, right? But those in the market is 1 year and more because they already stabilized. So basically, we have tried gold nanoparticle 3 years also stable. Okay, so it's okay. So biomedical application of it, gene drug delivery, optical imaging, for CT scan, and also for biosensors. So meaning that you can use all gold nanoparticles for all these patients. So it depends on what are the modification that you actually do it. Okay, other potential application, immunosensor, X-ray contrast agent, DNA, okay, sensors, immunosensing, sugar sensor, anything, many types of sensors and biosensors can be used. Okay, these are the size wise. Okay, so for research life science, okay, you can use 4 to 15 nanometer. For sensors, normally we use 50 up to 80 nanometers. You can also use like light scatter or absorbent properties. Normally people use 60 to 80 nanometer. Okay, research, it's lots of range of can be used for research. Okay, these are the disease that I showed before, mostly use low nanoparticle. So meaning that you conjugate with whatever biomolecules, what are the diseases you can actually have. This one has been reported or commercialized. Okay. Okay, so these are in lab how it looks like for nanoparticle. Color wise, you can change basically. So that's why some lipstick you can see is red, some is purple or slightly bluish because of change in this. And it also can be caused by agglomeration. So that's why the best is red. Okay. Shapes you can always change, dimension you can always change. Okay, this one is just to show how it looks like. Okay, the size you can always change. Okay, this is drug delivery system that we have done before. Okay, so basically the color is depends on drugs, both TB drugs for this. Okay, so we give you drug delivery system of different color. So the concept is similar with what I show you. We put the drugs inside, right? And then this is we can use to view in the cell. I can see directly. Okay, that's all my lecture today. Any question? Have you seen the assignment? Okay, so you can choose any types of disease that choose the diagnostic kit to actually do that. So you discuss what are the nanomaterials, and then you have to conjugate with what to detect what disease. Because I want to see what are the formats there is. Okay?
What's to include nanomaterials?
Yeah, you can choose because in my lecture, I mentioned gold nanoparticle, I mentioned iron oxide nanoparticle, I mentioned quantum dot, I mentioned. But from literature, there are many, not limited to gold, but I would say agent.
Yes.
Go. Go.